So section 9.6, this is the last section that we'll be doing. And this section is about minimum maximum value of a function. And the key point of this section is to determine when the function has a local minimum, maximum, and saddle points. So let me just say calculus 1. Calculus 1, we study functions of one variable. So f of x equals y, function of one variable. So for example, I may take this function f of x equals, let's say, for example, x squared. So here's how the function looks like. F of x equals x squared. The function looks like this. It's a parabola. So the function has minimum value at 0, and that's a simple function. We can see that, but the way we can determine this, if the function would be more complicated, then what we could do is we could compute derivative of this function f. Okay, derivative of this function f is 2x. Derivative of this function f is 2x. And first I want to look at the equation 2x equals 0. I want to know for what points of x derivative is 0, this will be 0. Those are the critical points. The unique solution to this equation is x equals 0. So the first derivative, what information we can get from the first derivative? The first derivative will give me critical points, i.e. the points when the function might have minimum or maximum value. But now, let's take those critical points and let's test them for minimum or maximum value. So for this one, we have the second derivative test, and let's compute the second derivative of this function. Well, the function was x squared. First derivative is 2x, and the second derivative of 2x is 2. And then I have to take the critical point. There's only one in this example, and I have to see what the second derivative of this point is equal to. See, the function is no matter what the input x is, the output is going to be always 2. So f double prime of 0 is going to be always 2, which is a positive number. So this is exactly the second derivative test. Because this is positive, so this is the second derivative test. Because the number is positive, the function has a local minimum at 0 at the critical point. Well, if you get the second derivative is less than 0, then you'll have a local maximum. But what could happen is that the second derivative could be equal to 0. So for example, take this function f of x equals x cubed. So how does the function x cubed looks like? This is the x-axis, this is the y-axis, and the function x cubed looks like something like this. I can't draw this exactly, but approximately that's how the function x cubed looks like. Okay, let's find critical points. For this, we have the first derivative. So let's compute the first derivative. The first derivative of this function is 3x squared. 3x squared. And let's solve this equation 3x squared equals 0. That will give me critical points. So that's the same as x equals 0. There's only one solution to this equation, and namely x equals 0. So that's what the first derivative will tell me, that 0 is the only critical point of this function. Let's test this point using the second derivative. So let's compute the second derivative prime of this function. Okay, so let's see, what's the derivative of this function? That's going to be 6x. The second derivative of this function is 6x. And let's compute the second derivative of this function at the critical point, which is 0. And see, because the second, okay, so what is the second derivative at 0? The second derivative at 0 is equal to 0. This will tell me, well, the function has, in this example, the function has no local minimum at 0, no local maximum. So in a way, that's kind of like a saddle point, and we'll generalize this in a second. So when the second derivative at the critical point is equal to 0, then anything could happen. The test is inconclusive. We'll have to use different methods basically to test this. Okay, so that's what we know. Now I want to do exactly the same, but for functions of two variables. So let's say we have a function f, and now my function is a function of x and y. So it's a function of two variables, x and y. And I want to see, so this is the situation. We have some function of x and y, something like this. And we want to see when the function has local minimum, when the function has local maximum, where the function has a saddle point, and so on and so forth. Okay, so this is my function f. Again, my function f is given, f of x, y. This is a given function. So first, we have to use first derivative and then second derivative, the two steps. So let's compute the first one, the first derivative of this function, but now with respect to x and y. Let me see, I think there are some people in the meeting room. Okay, admitted. So let's compute the first derivative of this function f with respect to x. This is a function of x and y. And let's compute the y derivative of the same function with respect to y. Well, it's a function of x and y. So given a function, I can compute the x derivative and the y derivative. Both of those two functions are functions of x and y. So I can take this function fx, and I can compute the x derivative of this function, or I can compute the y derivative of this function. So this is the second derivative fxx. This is the second derivative xy. And exactly the same thing here. This is a function of f of the derivative of this function f with respect to y is a function of x and y. So I can take this function fy, and I can compute the x derivative of this function as well as the y derivative of this function. So now I have four functions, fxx, fxy, fyx, and fyy. So I have four functions. Those are the second derivatives of my function. In one variable, there's only one second derivative. But if the function has two variables, we have two first derivatives. So this is the first derivative, two functions. And the second derivative is actually four functions. And we can arrange those four functions in the following way. We can look at them in the following table, really. So this is the fxx function, so this one. This is the fxy function, so that's this one. And then in the 2-1 position, we have the fyx function. And finally, in the 2-2 position, or 2-2 entry, we have the fy1 function. So this is, we can think of this as a 2-by-2 matrix of functions and call this matrix H. Notation for this is H, and this matrix is called the Hessian matrix of this function. F Hessian matrix is simply matrix of second partial derivative of this function f, and there's four of them. So now I have to compute the determinant of this matrix. Let me very quickly remind you, if I have any matrix, for example, A, B, C, D, A, B, C, D, then the determinant of this matrix is A times D minus B times C. It's a number, B times C. So I can compute the determinant of this matrix. So it would be this function times this function, and then minus this function times this function. This is the determinant of this function. Now, however, one thing to notice is when the function is f is nice and continuous, and so are the partial derivatives, then the mixed partial derivatives are actually equal. So, in fact, this matrix of this matrix would be exactly the same as this matrix of that matrix. And so the determinant of this matrix is this function times this function minus this squared. And the reason is this squared is because of the symmetry. Well, and then we have the second derivative of this. When the derivative is positive, and so is the first entry. So if the determinant is positive, and so is the first entry of this matrix, then we have a local minimum. So that's the case. This is a local minimum. Okay. This is a local minimum. Now, when the determinant is positive, but the first entry of this matrix, so A, is negative, then we have a local maximum, and that's the case. This is the local max. This is the local maximum, and when we have the case when the determinant is negative, then at this point A, the function has what's called a saddle point, and saddle point looks like this. So this is a saddle point, this point right here. Notice one thing, when you compute the x derivative, the tangent line is going to be 0, and the y derivative is also 0. But then we have no maximum, so here there's no max and also no minimum. The function has no maximum, no minimum. Actually, on your face here in the nose and your eyes, there's a saddle point. So, okay, specific example. Let's take this function f of xy. Take this function f of xy equals y squared minus x squared. Okay, so here, what we have, the function looks like this, and obviously we can see right from the graph that this is going to be a saddle point of this function. But let's say, for example, let's say that the graph is not available, and maybe the function is much more complicated than this one. Maybe the function is much more complicated than this one, and still we'll like to see where's the saddle point, where's the minimum, maximum. There's no minimum. In this example, there's no maximum, and there's only one saddle point, and let's try to compute this formally. Well, even though we can see what's going on because the graph is given, but let's say we didn't know that. So, okay, so here's the function f. So step one would be find critical points. Step one, find critical points. Find all critical points. What are the critical points? Critical points are when the function might have local minimum, maximum, or saddle. So let's see. How do we find critical points? First derivative. But first derivative will give me two functions because my function is a function of x and y. So the first derivative of my function f with respect to x is a function of x and y. Let's compute very quickly derivative. What is derivative of this function with respect to x? So could I ask you this question? What would be derivative of this function with respect to x?
Negative 2x.
Excellent. Negative 2x. Negative 2x. Let's compute now the y derivative of this function f. In other words, derivative of this function f with respect to y. So let's compute very quickly. Can I ask you this question? What is the y derivative of this function?
2y.
Excellent, 2y. Okay, so those are first derivatives. So now let's look at this equation. Negative 2x equal 0, and also 2y equals 0. So now we have really not one equation, but system of two equations. So we have the system of two equations, and let's solve the system for x and y. What is the unique solution of the first equation? For what value of x negative 2x is 0?
X equals 0.
Excellent. For x equals 0. Let's solve the second equation. For what value of y, 2y is 0?
Y equals 0.
Excellent. Y equals 0. And that will give me one critical point. Only one critical point, namely the point is x equals 0, and y equals 0. So since we are already, the domain of this function is the collection of all the real, the two-dimensional space. This is the domain of this function, two-dimensional space. Everything is in the domain of this function, and there's only one point in the domain of this function, which is a critical point, namely this point 0, 0. 0, 0. Now let's see.
Professor, I think someone's in the waiting room.
Oh, thank you so much for letting me admit. Thank you. So let's see, we have only one critical point, which is 0, 0. So now I have to use second derivative. So now I have to compute second derivative. So let's see, I don't know if we can find some room in here. But okay, this is my first derivative with respect to x. This is my first derivative with respect to y. Okay, so now let's take this function fx. Let's take this function fx, and let's compute the x derivative of this function. So fxx of y. And I'm going to ask you this question. What is the derivative of this function negative 2x with respect to x?
Negative 2.
Excellent. Equals negative 2. And let's compute, take this function fx again, take this function fx again, this function, but now let's compute the y derivative of this function. Well, okay, there's no y. The y derivative of this function, think of this as a constant, so derivative of constant is 0. Okay, so those two, this is the x derivative of this function fx, and this is the y derivative of this function fx as well. Okay, so now let's look at the other function fy, and we have to do the same thing. This is the function fy, and I have to take this function fy, and I have to compute the x derivative of this function. So let's see. The function is 2y. What is the x derivative of this function? Again, there's no x. This is constant, so it's 0. Okay, and the last thing to do, take this function fy again, but now let's compute the y derivative of this function. So x comma y equals, okay, so let me ask you this question. What is the y derivative of this function 2y?
2.
Exactly, so that's equal to 2. So now let's look at the Hessian matrix. The Hessian matrix H of xy, the Hessian matrix H of xy is going to be equal fxx of xy, fxy, and then fyx, and finally fyy. So in this specific example, let's see what's fxx. This is negative 2. Okay, fxy, this is 0. Fyx, also 0, and no surprise, this is symmetric, so also 0. And fyy, this is equal to 2. Okay, this is equal to 2. So let's compute very quickly the determinant of this matrix. The determinant of this matrix is negative 2 times 2, which is negative 4. The determinant of this matrix H of xy. Well, okay, so now what I have to do is this is the function H of xy. But really, now I have to take this function H of, and I have to take the critical point, 0, 0. Well, but that's very simple because it's actually the same matrix. But So when x is 0, the entry doesn't really depend on x. So this is -2, this is 0, and this is 0, and this is equal to 2. And last question, let me ask you this question. What is the determinant of this matrix?
-4.
Excellent. Determinant of this matrix, so let me squeeze it here. Determinant of this matrix H is equal to -4. So at this point 0, 0, we have a saddle point. And indeed, this is the saddle point at 0, 0. When you look at this test, see, determinant of this matrix was -4, so that was something negative. Determinant was negative. So when this is the case, the determinant of this matrix is negative, at this specific point, in my example at 0, 0, then at this point 0, 0, we have a saddle point. So 0, 0 is a saddle point of my function. So let me just show you again the same example, but now my handwriting was not that good, so let's go over the same example very quickly. So the function was f of xy equals x squared or y squared minus x squared. This is my function f. That's the given function f. And first thing to do, let's find the critical points. Maybe there'll be one, but let's see. Let's find the critical points of this function. What we have to do, critical points, first derivative is for that. So let's compute the x derivative of this function f. In other words, the derivative of this function f with respect to x. This is -2x. And let's take now this function f again, and let's compute the y derivative of this function f. In other words, the derivative of this function f with respect to y. The derivative of this function with respect to y is 2y. Okay, so we have the x derivative, and we have the y derivative. And now I can look for the critical points by solving this equation. The first derivative, -2x equals 0, and then 2y, this is 2y equals 0. The only solution of this system of equations is x equals 0, y equals 0. So the point 0, 0 is the only critical point of this function f. We'll be testing this point because we would like to see what do we have at this point. Is it minimum, maximum, or a saddle point? To do this, let's compute the second derivatives. So take this function fx, and compute the x derivative of this function as well as the y derivative of this function. That will give me the function fxx, which is -2, and that will give me the function fyx, which is 0. The same thing, take this function fy, and let's compute the x derivative of this function as well as the y derivative of this function. That will give me fyx, which is 0, and fyy, which is 2. So now let's find the Hessian matrix of this function, and then let's evaluate this Hessian matrix at this point 0, 0. Okay, so for any point xy, the Hessian matrix looks like this. This is the fxx, fyxy, fyx, and fyy. This is the Hessian matrix. In fact, it doesn't really depend on any inputs because the Hessian matrix is a constant, so this is -2, 0, 0, 2. This is the Hessian matrix. This is the Hessian matrix of second partial derivatives of this function f. Now let's evaluate this Hessian matrix at 0. So my Hessian matrix this is for any point xy, but I want to evaluate this matrix at the critical point 0, 0. In fact, the entry doesn't really depend on x and y, so simply it's the matrix -2, 0, 0, and 2. And let's compute very quickly the determinant of this matrix. The determinant of this matrix is -4, and this is a negative number. So because of the second test, we know that 0, 0 is a saddle point of this function f. And indeed, when we sketch a graph of this function f, it looks like this. And we can see that at 0, 0, the function has no minimum and no maximum, but it has a saddle point, which looks like this. And I want to give you one more example of the same kind of situation. Question is exactly the same. Question is this: find the local maximum and minimum values of a given function, and also find saddle points of a given function. And the given function is this one. The given function is f of xy, x to the fourth plus y to the fourth minus 4xy plus 2. See, this is how the function looks like. However, without this graph, it would be very difficult to say where the function has local minimum, local maximum. Looking at the graph is obvious. Well, here is local minimum, here's another local minimum, and here is saddle point. Looking at the graph is obvious, and I know that. But the point is that when the graph is not available, that would be not so easy to say right away where is the local minimum, maximum of this function. But we have this very nice method. First step is to find critical points. So I have to compute the x derivative of my function, f, xy. Okay, so let's compute together the x derivative of this function f. Derivative of this is 4x cubed. 4x cubed. Derivative of y cubed with respect to x is 0, and then minus 4xy. Derivative of this portion of this function with respect to x is negative 4y. Negative 4y. Okay, so this is my x derivative of the function. Let's compute the y derivative of this function. So the y derivative of this function, in other words, the derivative of this function with respect to y, is the following function. So derivative of this with respect to y is 0. Derivative of this with respect to y is 4y cubed. 4y cubed. And negative 4xy. What is the derivative of this function with respect to y? Is going to be negative 4x. Negative 4x. And 2 is a constant. Derivative of constant is 0 with respect to x and y. 2 is a constant, so derivative of this portion of this function is 0. Okay, so I have the first derivative of my function f with respect to x, and I have the first derivative of my function f with respect to y. This will tell me where are the critical points. This will tell me where are the critical points. When you think of this, one is going to be at this point because the tangent plane to the graph of this function is a horizontal plane. So when we draw the tangent plane to the graph of this function, it would be a horizontal. Also, the tangent plane to the graph of this function at this point would be horizontal. And well, at this point we'll get minimum, at this point we'll get maximum, and at this point right here, the tangent plane is also going to be horizontal. But see, just knowing that the tangent plane is horizontal won't tell me I have minimum, maximum, or saddle point. For this, I have to look at the second derivatives. The first derivative, which are two functions in this example, will just give me critical points. So let's look at this equation f x equals 0 and f just x, first derivative. Fx equals 0 and fy equals 0. Let's solve this equation for x and y, and that will give me 3 points. One is going to be here, one is going to be here, and one is going to be here. Okay, so let's see. So I'm looking at this equation. The first one was 4x cubed minus 4y equals 0. That's the first equation. And the second equation is 4y cubed minus 4x is equal to 0. Okay, so this is system of two equations. Let's look at the first equation, and maybe let's rewrite this equation in the following way. First of all, divide by both sides of this equation by 4, and I get that x cubed is equal to, well, if I put the y on the right-hand side of this equation, then I'll get that x cubed is equal to y. And let's look at the second equation now. Divide both sides also by 4, because the 4 is just constant, and we don't need it for anything. So we get that y cubed is equal to, well, what is going to be the right-hand side of this equation? Y cubed is going to be equal x, exactly. Okay, so now let's say that y is equal to x cubed. Now let's say that y is equal to x cubed, and let's fix this equation and use this equation and substitute to the second one. So substitute this equation to the second one. So if y is equal to x cubed, then here we have y is equal to x cubed. See, y is equal to x cubed. But then I have to cube this again, and that is equal to x. The right-hand side of this equation, that's equal to x. So I have really x to the 9 equals x. Okay, so now this is a question for you. Could you give me all solutions to this equation, x to the 9 equals x? What points of x satisfies this equation? For example, if you take x equals 0, then this point x equals 0 does satisfy this equation, because 0, 9 is 0. Also, if you take x equals 1, does this point x equals 1 satisfy this equation? Yes, because 1 to the 9 is 1, so that's okay. Could you give me one more solution to this equation? X equals what point?
-1.
Excellent. There's one more solution, namely x equals -1. Perfect. Those are the three solutions to the second equation. Okay, so let's take so now let's consider the three cases. Case 1 would be when x is equal to this one, 0. Okay, but if x is equal to 0, let's look at this equation. If x is equal to 0, what is the corresponding y?
0.
Excellent. Y equals 0. So we have one critical point, namely this point is 0, 0. Okay, let's look now at the second case. So the second case would be when x is equal to 1. When x is equal to 1. Okay, when x is equal to 1, could you tell me what is the corresponding y?
One.
Excellent. Y is also 1. So we have another critical point, 1, 1. And lastly, let's take the last case, when x is equal to -1. That's this case. When x is equal to -1, what is the corresponding y? Okay, what is the corresponding y when x is equal to -1? Excellent. -1, so we have another point, -1, -1. Okay, those are the critical points. So how many critical points do we have? 3, because one critical point is 0, 0. So let's draw them on the xy plane. This is the domain of this function, this is the x-axis, this is the y-axis, and one point is 0, 0. This is a critical point. Another one is 1, 1. So here's 1 and here's 1, another critical point, and another one is -1, -1. So here's another point. Okay, so all the 3 points, they lie on the straight line y equals x, but we have only 3 critical points. So what do we have to do now? I have the 3 critical points. I have to construct the Hessian matrix and evaluate this matrix at those. So I have to construct the Hessian matrix, and now I have to consider 3 cases. I have to test all of those 3 points. Take the Hessian matrix and evaluate this Hessian matrix first at 0, 0. Then take the Hessian matrix evaluated at 1, 1. And take the Hessian matrix evaluated at -1, -1, and use second derivative test. Let's do that. So, okay, so maybe, okay, we have time a little bit, so let's compute the Hessian matrix very quickly. So for this, I need second derivatives. Okay, for this, so far what we have done is this. The function f was given, that was the function f. We have computed the x derivative of this function, and that's the function f. We have done that. We have also computed the y derivative of this function, and that's the function fy. Also, we have done that. And then we look at this equation. First derivative equals 0, and second derivative and y derivative also equals 0. We have solved the system of linear equations, and we've got 3 critical points. This is the point 0, 0. This is the point 1, 1, 1, 1, and this is the point -1, -1. Okay, now let's take this function fxx, and let's compute the second derivative very quickly. So take this function fx, and let's compute the x derivative of this function. Is a function of x and y. Okay, so what is derivative of this function with respect to x? This is going to be 12x squared. 12x squared. And let's take the function fx again. But now let's compute the y derivative of this function. So let's see, the y derivative of this portion of this function is 0 and -4 y. With respect to y, this is -4. Okay, this is -4. Okay, this is the function fxx. This is the function fxy. And I have to do the same. I have to look now at the other function fy. So I have to look at fy, and I want to compute the x derivative of this function. So let's see, this with respect to x, this is going to be -4, and I have to take again this function fy and compute the x derivative, or now the y derivative of this function. So let's see, the y derivative of this function is going to be 12y squared. 12y squared. Okay, so this is the fyx derivative, and this is the fyy derivative. So now let's look at the Hessian matrix. Let's look at the Hessian matrix at any point xy. At any point xy. So the matrix looks like this: fxx, fxy, and then fyx, and then fyy. So in my specific example, the fxx function is 12x squared, 12x squared, and then fxy is -4. fyx is also -4. This is symmetric, so no surprise here. And fyy is 12y squared. 12y squared. Okay, so this is my Hessian matrix X. Let's evaluate this Hessian matrix at one of those critical points. Let me do it at 0, for example. So when x is 0 and Also, when y is 0, then what matrix do we have? This is 12 times 0, which is 0. And this is negative 4. And then this is negative 4 again. And this is 12 times 0, which is 0. Okay, let's compute the determinant of this matrix. Determinant of this matrix H. This is going to be 0 times 0, which is 0, minus negative 4 times negative 4. So negative 4 squared. This is equal to 0 minus negative 4 squared. What is negative 4 squared? 16. So this is equal to negative 16. And because derivative of the Hessian matrix at 0, 0 is a negative number, this means that at 0, 0 we have a saddle point. And then we have to do the same. We have to take this matrix H of xy and see what this matrix is equal to at 1, 1. And then see what this matrix is equal to at negative 1, negative 1. So let me do this a little bit better. So we'll speed up a little bit. So again, the function was f of xy equals, that was the given function. Remember, we have already found the critical points. One was this point 0, 0. Another critical point was 1, 1. And another critical point was negative 1, negative 1. So we have found this critical point. And for those critical points, how do we find the critical points? We use the first derivative. The first derivative will give you critical points. We have 3 in this example. Now I have to test all of those 3 points using the Hessian matrix. So if this is my function f, first of all, compute the x derivative of this function. And we have done that. And compute the y derivative of this function. We have also done that. So this is the x derivative, and this is the y derivative. Now take this function fx and compute the x derivative of this function and the y derivative of this function. That will give me second derivatives. This is the function fxx, and this is the function fxy. This is the function fxy. Similarly for the other function fy. Take the function fy and compute the x derivative and the y derivative of this function. Okay, that will give me the Hessian matrix. The Hessian matrix has 4 entries, and the first of which is fxx, the other one is fxy, fyx, and then fyy. This is the function 12x squared, negative 4, and 12. The matrix is symmetric because the function was continuous. Okay, so now take the Hessian matrix, evaluate this Hessian matrix at 0. That's the matrix 0, negative 4, 0. Determinant of this matrix is negative 16. And this is a number that's less than 0. And because it's less than 0, at 0, 0, the function f has a saddle point. At 0, 0, the function f has a saddle point. Let's do the same with the other critical point. Now take the other critical point 1, 1. Take the other critical point 1, 1. And evaluate the Hessian matrix H at 1, 1. So we have this matrix 12, negative 4, and 12. The determinant of this matrix is 12 times 12 minus negative 4 squared. So that's 128. And this is a positive number. This is a positive number. And also the 1, 1 entry of this matrix is also positive. The 12 is also positive. So because we have those two things, the 1, 1 entry of this matrix is positive, and so is the determinant of this matrix. Because of that, at this point 1, 1, the function f has a local minimum. So at this point, we have local minimum. And last thing to do, take the other critical point, which was negative 1, and see what the Hessian matrix, look what the Hessian matrix at this negative 1 -1 point looks like. So the general Hessian matrix, here it is. And let's take x and y equals -1 and -1. So the one, again, the same matrix. So this is 12, -4, -4, and 12. The 1 entry of this matrix is positive, and the determinant is also positive, is 128. So at 1, 1, the function f has also a local minimum. So also a local minimum. And at 0, 0, the function has a saddle point. So at 0, 0, the function has a saddle point. So that's all information. We have 3 critical points, namely 0, 0, 1, 1, -1, -1. First derivative will tell me about the points, and the second derivative will tell me do we have local minimum, maximum, or saddle point. At 0, 0, we have saddle point because the derivative of this matrix is negative. At this point, 1, 1, we have minimum, and at this point, -1, 1, also we have a minimum. And this is all what I wanted to say for today, really.